So we last looked at solving systems of equations graphically, by graphing the lines, seeing if they cross, if they don't cross. Today we're going to do it algebraically, so you probably should remember doing this once before, at least. There's two techniques that we often use when we're solving systems algebraically. The first is substitution. When you're doing substitution, we're isolating one variable and then solving for that one variable to solve for the other variable. The idea is you have two equations, two unknowns. The other technique is to use elimination. In that case, you're going to take two equations and you're going to add them together or subtract them from each other in such a way that you can get one of the variable to disappear or be eliminated. So here are some examples. This one we're going to solve by substitution. The key to solve by substitution is to look for an equation that has a single variable without a coefficient ideally. So for example, the x plus 4y equals 26. That's a dead giveaway to use substitution because you're going to just solve for x. So if I solve that first equation for x, I'm going to get 26 minus 4y is equal to x. And then I'm going to take that value and I'm going to plug it into my second equation where I see the x. So I'm going to plug 26 minus 4y in for that x in the second equation and then rewrite it and solve for y. Then I have one equation in one unknown, and so I can solve it. I'm going to go ahead and simplify. 26 minus 9y is equal to negative 10. Subtract 26 from both sides. Negative y equals negative 36. Divide both sides by negative 9, and I'll get y equals 4. Now, I'm not quite done. I've got one variable, so now I need to get the other one. I'm going to take that y value and plug it into one of my equations to solve for x. So I'll stick it into the second equation. You could stick it into either one and you'll get the same answer. But I plug 4 in for x. X minus 5 times 4 equals negative 10. And I'll solve and get x minus 20 equals negative 10. Add 20 to both sides. And I'll get x equals 10. So if I want to write it as an ordered pair, x is 10, y is 4, and that would be my final solution. If I plug those numbers into either or both equations, they should check. I'm not going to do that right now, but please do that on your own and check to make sure they work. Okay, here's a word problem. So this is another type of problem you might see. Lulu's Furniture Company builds two types of wooden outdoor chairs. A rocking chair sells for $265, an Adirondack chair with a footstool for $320. Last month the business earned $13,930 for the 48 short chairs sold. So we're going to set up two equations in two unknowns, and then we're going to solve. Now the first thing we know is we spent $13,930. We're going to describe R as the number of rocking chairs that were sold and A as the number of Adirondack chairs. And so we can write an equation that represents how much money we actually spent. So since it cost $265 for an Adirondack chair, we can say that 265 times R, hang on. Okay, yeah, 265 times R, because that's the cost of a rocking chair, plus 320 times A, and that's going to equal the total cost, $13,930. Now, what other equation could we find? Well, we know that 48 chairs were sold altogether. So if the number of rocking chairs plus the number of Adirondack chairs has to add up to 48, we just get R plus A is going to equal 48. Now that's a perfect problem to use solving substitution. I can get R all by itself really easily, 48 minus A. I'll take that and plug it in for R in the other equation. We're going to get some pretty big numbers, but with a calculator it shouldn't be too hard. So I go ahead and add 48 minus A in for R, plus 320A equals 13,930. I distribute the 265, and now I'm just in the simplifying process. Calculator is going to be handy, working through these. I simplify my A terms. 55A equals 1210, or A is 22. So I sold 22 Adirondack chairs. We know that all the chairs have to add up to 48, so now I can solve to figure out how many rocking chairs that is. It's going to be 48 minus 22, or 26. So now you know how many chairs of each. Okay. The other technique we're going to talk about is solving for elimination. And by using elimination, we want to eliminate one of the variables. Now in this case it's really nice because we have a 2y in each of the equations. So all we have to really do is take the first equation and subtract from it the second equation. And the y terms are going to disappear because 2y minus 2y is 0. So I'm going to go ahead and subtract the second one. Remember, you can add or subtract depending on what you want to do, whatever's most convenient to get this what you want. When I subtract, I get x equals -4. Now that I have x equals -4, I can plug it back into either one of the equations, plug that value in for x, and solve for y. So I'm going to go ahead and plug it into the first equation, 3 times -4 plus 2y equals 8. So now I'm going to solve for y. -12 plus 2y equals 8. Add 12 to both sides. 2y equals 20. Divide by 2, y equals 10. So now I have both solutions. I can express them in as an ordered pair of -4, 10. All right, now I don't have any variables that I can just add or subtract and one's going to disappear. So I actually have to multiply one of the equations, or maybe both of the equations, in order to get one of the variables to disappear. So in this case, I'm looking at the 3y and the -2y, and I'm thinking, I want to multiply the top equation by something and the bottom equation by something so I can get those to disappear. So I'm going to multiply the top equation by 2 and the bottom equation by 3, and I'm going to rewrite each of them so that I don't make a mistake. So the top equation becomes 4x plus 6y equals 24. Again, I multiplied that whole equation by 2. The goal here is to get both equations to have a 6y in them and then subtract one from the other so the 6y's will go away. When I multiply the bottom one by 3, I get 15x minus 6y equals 33. So now once again I have a 6y term and a -6y term. If I then add these two equations together, the plus 6y and the minus 6y, they will cause the y's to go away, and I'm left with just x's. And that's my goal. I want the y's to go away. I add them together. I get 19x equals 57. Divide both sides by 19, and I'll get x equals 3. Now I have to plug 3 back into one of my original equations. Either one will work. I'll choose to do the first one. 2 times 3 plus 3y equals 12. Solve for y. And y equals 2. So my ordered pair is 2, 3. Looks like I didn't write it. Let me write it right now. 2, 3. Okay. Oops, I did write it. Oops, I wrote it wrong. Hold on, let's fix that. The ordered pair is 3, 2. 3, 2. There we go. All right. Let's go on to the next one. Not every system of equations, as we found when we were graphing them, comes up with a solution. So remember, for example, if we had parallel lines, we never got a place where they intersected, so we didn't get a solution. So let's look at what that looks like algebraically. So here we have two equations. Again, I want to try to solve by elimination, so I'm going to take the top equation and multiply it by 2 so that I can get those x terms to drop off. I'll rewrite the equation though. I get minus 6x plus 10y equals 24. So the first equation I've rewritten down here below in red. Now I have these two equations, and so I want to combine them, either adding or subtracting them, to get one of the terms to go away. So I'm going to go ahead and add them so that x terms go away. When I do that, I get 0x, oh, and the y terms go away too. So I end up with a 0 is equal to 3. And you have to ask yourself, for what value of x or y is 0 ever equal to 3? And the answer is there is no value. There is no such thing. So there would be no solution in this particular case. And just so you know, the reason that's true is because if you were to graph these two lines, you would find that they are parallel. Now, I didn't graph them exactly, but that's the idea. There'd be parallel lines, so they're not going to give you any solutions. You would say that they are independent and inconsistent. Okay, so some equations you're going to get an infinite number of solutions. So remember when they had the overlapping lines and we called them dependent? That's what it's going to look like. Let's solve that algebraically and see what happens. I'm going to choose to use the substitution method because I have a y all by itself. So I'll solve for y, get 1/4 x plus 6. I'm going to take that whole value and substitute it in where I see y in the upper equation. Y equals 1/4 x plus 6 is equal to 2x plus 48. Now I'm just going to simplify and solve for x. Okay, so I get 2x plus 48 equals 2x plus 48. So if I subtract 2x from both sides, my x's go away. If I subtract 48 from both sides, my 48's go away. I end up with 0 equals 0. Well, when is that true? That is always true. So this is a case where you have infinite solutions. And if you want to understand what's happening graphically, that just means that you have overlapping lines, or they're dependent and consistent. Okay, now I have a couple practice problems here, so I want you to, on your paper, go ahead and try to solve these algebraically, choosing the method of your choice, figure out which one would be the best way to solve it, and then I will reveal the answer. So pause the video and work this problem, and then I will reveal the answer. Okay, I'm back. I chose the substitution method because I had that x all by itself. I plugged that value in for the x in the upper equation, and I solved and found that y equals 9. I plugged that back in to one of the equations, and I found that x equals -7. So the ordered pair would be -7, 9. Okay, last problem coming up. Here's another practice problem in U and V, so go ahead and figure out which technique you want to use and solve the equation. And pause your video, and then I'll review the answer when you come back. Alrighty, so I decided to multiply the top equation by 2 and the bottom equation by -3. That way I get a 6u and a -6u down below, and the u's will go away when I add the two equations together. So I'll add them up. You could have done it many different ways, but when I go ahead and solve, I get v is 33/22, or 3/2. I take that value and I plug it in for u, and I do it to the second equation. When I plug it in, I solve for u, and I found that u is -1/2. I plug both of those answers in to see if they work. I just want to double check, and in fact they do check. So the ordered pair for this one would be -1/2 and 3/2. If you're wondering what order to put the ordered pair when it's not x and y, just do it alphabetical. So u comes before v, so the -1/2 would come before the 3/2. And that's it. We're done.